Why is robot kinematics computationally costly? Imagine trying to solve a puzzle where each piece moves in complex ways, and you need to figure out exactly how to fit everything together. That's what robot kinematics is like. It involves calculating where each part of a robot is and how it moves based on joint settings. When you want the robot to reach a specific spot or move in a certain way, the calculations get tricky. The main reason it takes so much computer power is because of the complicated math involved, especially when figuring out how to get the robot's end effector to a desired position and orientation. This process is called inverse kinematics, and it's often nonlinear, meaning the equations don't follow a straight line. Instead, they twist and turn, making them harder to solve. To find solutions, engineers use iterative methods that try different guesses over and over until they get close enough. This takes time and processing power. Robots with many joints, known as high degrees of freedom, add even more complexity. They can move in many ways to reach the same point, creating a lot of redundancy. To pick the best way, algorithms need to optimize the joint angles based on criteria like energy use or obstacle avoidance. This adds layers of calculations. Plus, real robots have physical limits like maximum joint angles, speed, and acceleration. When solving kinematics, these constraints turn the problem into a constrained optimization task. Handling all these limits requires extra calculations, often using linear or quadratic programming, which are computationally intensive. Control systems demand that these calculations happen very fast, often within milliseconds, so the robot can respond to sensor inputs and adjust its movements in real time. Achieving this speed requires efficient algorithms and sometimes specialized hardware like digital signal processors or field-programmable gate arrays. But even with hardware help, the complexity of the math still demands a lot of processing power. Another challenge is ensuring the calculations are stable and accurate. Small errors can lead to imprecise movements or even collisions. To prevent this, algorithms often need iterative refinement, which takes more processing time. When you combine all these factors, nonlinear equations, multiple solutions, constraints, real-time demands, and accuracy needs, it's clear why robot kinematics is such a demanding task for computers. In practical terms, think about robotic arms used in factories. They need to position themselves precisely and quickly to assemble products. Or consider autonomous robots navigating busy environments. They must constantly recalculate their position and path on the fly. Electrical engineers work hard to optimize algorithms, improve numerical methods, and develop hardware that speeds up these calculations. They aim to make robot kinematics faster and more efficient without sacrificing accuracy. So, the reason it's so costly in terms of computation is because solving these complex, constrained, and nonlinear equations in real time takes a lot of processing power and clever engineering.